Hello everyone. Today let us try to look into practical. We have been seeing many properties of multivariate normal distribution. In fact, in theory we have reached the testing part also. So let us try to catch up in the practical also. So the first question is for bivariate normal. Mean vector is given, sigma is given, and we are supposed to obtain first a random sample of size 100 from this distribution. Of course, there are some what do you say ready-made commands, direct commands available in our packages which can be used for sampling from multivariate normal distribution, but we are not going to use them here. We will try to understand how we can sample manually. Okay, so in the univariate normal setup, you know that you can generate random observations from standard normal and then convert them to whichever normal you want. We are going to use exactly the same procedure here. We will generate observations from standard uh, multivariate normal, okay, standard multivariate normal, and then we will try to see that if we can convert them to whichever multivariate normal we want. Okay, so that is exactly what we are supposed to do in part 1. So this part A says obtain a lower triangular matrix T such that Tt prime is sigma and also compute the matrix manually, and then using this T we are supposed to obtain a sample of size 100 from this distribution. Okay, so so the sigma matrix that is given to me is this 2 minus 1 minus 1 5. So I'm supposed to find a lower triangular matrix T such that Tt prime is sigma. First of all, why I'm doing this? The reason is we know, just as I mentioned, we want to go from standard multivariate normal to general multivariate normal, and we know in theory we have seen that when you want to go from standard multivariate normal to general multivariate normal, what we know is square root of the variance covariance matrix. So this T can actually act like a square root of the variance covariance matrix. So if I want T such that this happens, and we are saying that T should be lower triangular, so T should be something like A, B, C, 0, right? So I want this into transpose of this. So A, B, 0, C, this should be sigma 1, 1, sigma 1, 2, sigma 1, 2, sigma 2, 2. Okay. So we have to solve this. So if I try to solve, I'm going to get A square, then AB, here also I'll have AB, and then B square plus C square. So this should be equal to sigma 1, 1, sigma 1, 2, sigma 1, 2, sigma 2, 2. Okay. Now, as you can see, this is symmetric. So this confirms that, okay, I'm not doing something drastically wrong here. So A square is sigma 1, 1. So that gives me A as root sigma 1, 1. Okay. Then AB is sigma 1, 2. So my B becomes sigma 1, 2 upon root sigma 1, 1. Of course, I am considering positive square roots only. And we know B square plus C square is sigma 2, 2. So C square is sigma 2, 2 minus B square, which is nothing but sigma 2, 2 minus sigma 1, 2 square upon sigma 1, 1. Okay, so now I have a way of computing A, B and C. Once I get this A, B and C, of course C would be square root of this. Once I get these A, B and C, I know that I have obtained my T, because my T is A, B, C, 0. Is it okay? Do you want me to actually do it here? Let us do it in R. Okay, now that we have these formulae ready, let us compute this T in R. Okay, so let us enter what are my values of mu and sigma. So mu is 4, 1. So mu is 4, 1, and my sigma is a matrix with entries 2, -1, -1, 5. Okay, I don't need to give by row equal to true because this is a symmetric matrix. So I want to compute T matrix. So we have just now derived the formula for T. So let me first create a blank matrix and then we'll compute entries one by one. So we know that T11, which was A in our notation, is square root of sigma 1 1. Okay, then T12 is 0 because my T is going to be lower triangular. T21 is sigma 1 2 divided by square root of sigma 1 1. Okay, and T22 is square root of sigma 2 2 minus sigma 1 2 square divided by sigma 1 1. Okay, I'm just copying the formula that we derived just now. Let us try to run these and see how my T matrix looks like. This is mu sigma T. Okay, so let me print T. So T is this. Confirm whether this T matrix is correct or not, we can try to compute T prime, and ideally if my calculations are correct, it should match sigma. So T into T prime. See, this is exactly sigma. This was the manual way of computing T. So when you have 2 cross 2, you can do that. As soon as you go to 3 cross 3, it becomes difficult because now you will have more unknowns. You'll have probably 6 unknowns in 6 equations, so solving it becomes difficult. And of course, for higher orders, it's going to be further difficult. So that's why we can also use a direct command available in R. So that's why in the question I have said both the things. So obtain a matrix first and also compute the matrix manually. So in this first part, you are supposed to obtain a matrix using R. So there is a command chol in R. Chol stands for Cholesky decomposition. So if you give chol of sigma, you actually get a matrix which is transpose of the T that we computed just now. So basically chol command gives me an upper triangular matrix, whereas what I want is a lower triangular matrix. So I can define my T as transpose of chol sigma also. Okay, this will give me exactly the same result. And this command would be helpful especially when I want to deal with higher order multivariate normal distributions. Okay, so this is my T matrix. So how are we going to use this T matrix actually to get the sample? So what we have seen in the theory is if I had Z1, Z2, Zn as IID NP 0I, that is they are coming from p-variate standard multivariate normal, then we know that I can define yi as mu plus t z, where this t is the t that we have computed just now. Say yi as mu plus t zi. What is the benefit of it? Expectation of yi would be mu. Expectation of zi is 0, so it won't contribute. Variance of yi would be, this won't contribute, so t times variance of zi t prime. We have seen this property, so this becomes t prime, and we know that t prime is sigma. So that is what we want, expectation to be mu, variance to be sigma. And because this yi is defined as some linear function of zi, yi also has normal distribution because that is property of normal. So this is exactly how we are going to use this T. So we are going to first get Z1, Z2, Zn from p-variate standard normal distribution and then transform those using mu and t to get yi. Now how to get these Z1, Z2, Zn? Because we know that each of them is standard multivariate normal, Actually, each Zi would simply be, say, Zi1, Zi2, Zip, where my Zij, each Zij is normal 0, 1, and all Zij's are independent because the variance coincidence matrix is identity matrix. There is no covariance between them. Okay, so what I want is, I just need to take P, a sample of size P from standard univariate normal, arrange them in the form of vector, that becomes my Zi. Got it? So if I finally want Z1, Z2, Zn, and we know that generally our data matrix is of n order n cross P, so I will have Z1, Z2, Zn arranged horizontally, so I can call them as prime. So basically I want n cross P matrix where every entry is coming from normal 0, 1. Okay, so these are P entries from normal 0, 1. These are again P entries from normal 0, 1. These are again P entries from normal 0, 1. That becomes my Z1, Z2, Zn, Z sample. And then from each of these, I will, so from these P, I will get Y1 by this formula. From the next P, I will get Y2 by the same formula, and so on. Is it okay? So let us do this in R. So what we are going to do? We are going to first get n cross P matrix consisting of univariate normals. Let me call it Z mat. Z mat is a matrix where n row is n col is P. I have not specified what are n and P, so n is 100 here, P is 2 because I want a sample from bivariate. Okay, and what I know is all entries in this matrix are actually sample coming from normal 0, 1. So I would say R norm, how many total entries? N into P. Okay, so entries in ZMAT are coming from univariate normal. That's why I'm not specifying, because if I don't specify mu and sigma, it takes 0, 1 by default, and I arrange them in the form of n cross P matrix. Okay, and now from each row of this Z, I need to compute Y. So let me define Y mat as again a matrix of same order. So n row equal to n col equal to P, and for I in 1 to n, for each row I have to do Y mat I, that is ith row of Y, would be mu plus T times ith row of Z. Okay, let us try to run this and see if we get the correct answer. Okay, I need to run this first, I'm sorry. Okay, so it didn't give me any error. Let me print first few rows of Y mat. So head of Y mat. Okay, this seems to be, does it seem to be reasonable? Yes, mean is 4, so these are roughly near 4. This mean is 1, so these are roughly near 1. A better way to confirm it would be to check the mean and variance of the new this new data. So I can compute call means of Y mat, and then, so this is C, this is quite near 4, 1, and then variance, so cov of Y mat, this is quite near 2 minus 1 minus 1 5. Okay, if you are still not sure whether it is near, you can try increasing n. As you increase n, it would be further close. So just for the sake of trial, let me make n as 5000. Oh, what is happening? I don't know why it is running again. There's some problem, my cursor went up and it started running again, and now it is stuck in a loop. Okay, anyway, see, now it is quite close to 4 1 and 2 minus 1 minus 1 5. Okay, if you increase sample size further, it would be further close. Okay, so this is how you generate a sample. I wrote a loop here, but it's not necessary. you can actually convert your mu also to a matrix by repeating mu those many times, and then you can use matrix multiplication to get y directly without using this. I'm leaving it as homework. You don't need R, you just need to write manually the equation where you can get entire n cross p matrix Y using an n cross p matrix Z. So if this is n cross p, this is n cross p, then this should be of order n cross p and this should be adjusted appropriately. If you cannot get directly n cross p, try p cross n and then you can take transpose. Okay, see if you can get p cross n matrix from here and then get a transpose. So okay, this finishes the second thing. And the third part says draw a bivariate density plot of the generated sample. So for computing density, I need the formula. So and then we will use that formula to get density and then we'll draw a 3D plot. Okay. First thing, I don't know whether you remember things from your first semester practical. Whenever you want to plot any distribution or density, generally it is not a good practice to use the sample that you have obtained, because sample may have underrepresentation of some areas, especially when your sample size is small. So a good practice is to take the quantiles, generally the 0.05th percentile. I'm saying, sorry, 0.5th percentile. I'm not saying 5th percentile. Okay, remember 0.5th percentile means I'm going even below first percentile. And then 99.5th percentile. So almost entire area is covered. And then try to take a sequence of equidistant point from that range. See, if you are computing density, or if you are drawing a plot for a distribution which has finite range, for example uniform, you can simply take the minimum and maximum. But in case of normal, you cannot take minimum and maximum because it's going to be minus infinity to plus infinity. So that's why you go for 0.5th percentile and 99.5th percentile, and then using those points you generate equidistant points within that limit and then compute PDF at each of those points and draw a graph. So here I would need same thing for both these. Okay, because I need to decide x-axis as well as y-axis, and z-axis would be the PDF. So I would compute quantile of, okay, I won't compute quantile from the sample, I need quantile from the normal. So q norm 0.005. Okay, because if I give 0.05, it would be 5th percentile. I want 0.5th percentile, where my mu is the first entry from mean and variance is, here you need to give standard deviation, not variance. So I would give sigma 11 square root of that. Okay, square root of sigma 11. Okay, this is your lower limit, and similarly you want upper limit also, so you can write this as comma 0.995. So what we are doing, we are trying to get 0.5th and 99.5th percentile of the first normal distribution, their limits of first. So L1, let me call them, oh sorry, sigma 11. R is not going to understand what I say unless I talk to it in its own language. Okay, sigma 11. So these are my limits. Okay, similarly I can compute L2 for second normal. So it would be sigma 22 mu 2. Should I change my view? This is better, I think. L2. So L2 turns out to be this. Okay, now I want to take equidistant points from these. So x1 be sequence from L11 to L12 of size 100. Okay, I take 100 points, and then y1 be sequence along y-axis. So L21, L22, okay, x1 and y1 I have run. Now we want to compute PDF at every such pair x1 y1. Okay, we want to compute PDF at every pair x1 y1, and then we will have z. And so to compute PDF at these points, let me first create a function which can compute PDF once we input x and y coordinates. Okay, so let me name that function as say by PDF. So by PDF is a function of x and y. I'm not going to use mu and sigma as the arguments because they are anyway available here in the environment. Okay, so the first term in my PDF is 1 upon root 2 pi. Okay, 1 upon root 2 pi. But here we have root 2 pi raised to 2 actually. So I would just have 1 upon 2 into pi and then square root of determinant of sigma. Okay, because 2 pi raised to p by 2 becomes just 2 pi. 1 upon square root of determinant of sigma. That is my first term. And the second term is actually the exponential term. So for that I need vector. So let me create a vector. So V is a vector constructed from x and y. And then my second term would be e raised to minus half into x minus mu, e raised to minus half x minus mu prime, then sigma inverse. So I'll have solve of sigma e raised to minus half x minus mu prime x minus mu. Okay, and now my next term is going to be t1 into t2 because I want that to be returned as my PDF. Okay, t1 into t2. First let us try to see if this works for some vector because sometimes R creates problems with this transpose and all. So let me run this function and try to see if it runs for some values. Oh sorry, control R. So let me try to give some random values between my limits. So have we printed? Yes. Okay, so 0 is in the range of both L1 and N2. So let me try to compute PDF at 0, 0. Yes, it does work and it does give me some value for the PDF. Now I have to compute PDF using this function for all possible pairs of xy, where x is coming from this vector x1 and y is coming from this vector y1. Now there is a command which can actually compute this. So one option is okay, you go by a loop. So you write two loops, I going from 1 to length of x1, j going from 1 to length of y1, and then at x1i, y1j you compute this PDF. That is one option which is a routine option, and of course you can stick to that, I don't mind. But this is a chance to learn a new command. So there is a command called outer. So what outer does is, given any two vectors, it will apply whatever function you give on every pair coming from those two vectors. So let me try something simple. So let me have say a equal to 1 2 and b equal to say 1 2 3. Okay, so these are two vectors, and let me now compute or print outer a b, and then the function that I am applying is addition. Okay, see the result. So what it did is, this is a, so all possible values of a are used here, all possible values of b are used here. So first 1 1, 1 plus 1 became 2, next is 1 plus 2, so 3, 1 plus 3 4, Then next row is for second element of A. So 2 plus 1, 3. 2 plus 2, 4. 2 plus 3, 5. So this is what outer does. So it takes these two vectors, creates all possible pairs, applies this function to them. Okay. So what we want to do is we want x1 here, y1 here, and then by PDF here. And let me store it in some matrix. Let me call it, say, fmat. It's a PDF matrix. So fmat be outer x1, y1, and by PDF. Okay. Okay. Now, why this error? See, the thing is, outer generally treats this entire x1 as a vector, y1 as a vector, and then tries to apply this function on a vector. Whereas the original function that we have written is to be applied on two scalars. Okay. So to avoid this problem due to scalar vector thing, there is a command called vectorize, which would enable outer to apply this command properly. Okay, so try to read help of vectorize also. It's a good exercise whenever you get, even if you don't have laptops, you can just Google and try to find our page, our help page for vectorize. See, with this now it is not giving an error. My x1 is of length 100, y1 is of length 100, so I expect the dimension of my fmat to be 100 cross 100. Okay, so dimension of fmat is 100 cross 100. If you want, we can just see for a bit. See, the initial values of PDF are very low. Somewhere in between they would increase. Of course, in between means both. So even V has to, in along horizontal direction also I have to scroll. See, somewhere V28 and then 38 here. Now we are getting reasonable values of PDF. Okay. Okay, let me minimize this. Yeah. Okay, what is happening? Okay, so now I have this this matrix of PDFs ready, and we are going to plot them. So for plotting, for 3D plotting there is a command called persp. So in persp you have to give x, y, and coincidentally for persp the z entries are to be given in the form of the matrix that we created just now. So all possible x1, y1 pairs and then corresponding values of z. So I will give my fmat here. Okay. See, this is the graph we get. Okay. So along this axis x1 values are increasing, along this axis y1 are increasing, and this is the z axis, that is PDF. Okay. There are some things that you can try. So for example, you can rotate this. So let me open help of persp and show you. We can rotate it. We can also get the entries on x and y axis. Right now there is nothing. So let us open persp help. Okay, so this is help of persp. You can see. Okay, so what I want is theta and phi will give me rotation. So let us read. Theta and phi are angles defining viewing direction. Theta gives the azimuthal direction and phi the co-latitude. Okay. And what other thing we want is names. So tick type. Okay. So tick type is, yeah, simple draws just an arrow. Detailed draws normal ticks as per 2D plots. So we want the ticks. So let me try tick type equal to detailed, and let us try theta equal to 30, phi equal to 30, and see what happens. Okay, so see this, now I am getting the scale here 246 minus 4 minus 2 and so on, and you can see the graph has been rotated. You can try different values of theta and phi and see how things change. Okay, so if I try theta equal to, let's say, 60, and then see what happens. See, the graph is further rotated. Okay, so you can give whichever way you like. Okay, so this is how we are going to draw 3D plot. So what new thing we learned today is outer and fmat. Okay, so I think this finishes question 1. Yes, question 1 is complete. In question 2, we have to find conditional distribution of x4 given this. Now actually this is not at all a difficult exercise. We already have formula for conditional mean and conditional variance with us. We have to just code that formula in R. So create x1 as this, mu1 as consisting of means of these three components, mu2 may be mean of this component, similarly sigma 11, sigma 12, sigma 22 and so on. Okay, so I am going to leave this as homework because this can be done even manually. So even if you don't have laptops, I would suggest try computing this conditional distribution manually. I think even the question bank has this as an exercise. This means not exactly this question, something similar, the question bank in theory. Same story here. The only difference is here the order was maintained. First three were given and you had to find the fourth. Here now first and fourth are to be estimated, or the distribution of first and fourth is to be found when you know second and third. So the only thing is you will have to first change your mu and sigma in such a way that your sigma 11 is consisting of one of these two parts, and mu 1 also consists of one of these two parts. Okay. Then question 3 is also not difficult. A is given, x is supposed to have same distribution that is given here. First question is find the distribution of y. Y is ax. So we know expectation of y would be a mu, variance of y would be a sigma a prime, and then the distribution is normal. So your job is just to compute a mu, a sigma a prime. So I think everyone can do it. Next is using eigen decomposition to obtain a matrix B such that sigma y is B square. So basically you have to find square root of sigma using eigen decomposition. This is exactly same as what we did in canonical correlation analysis. We tried to find square root of sigma inverse, sigma xx inverse or sigma yy inverse. Instead of inverse, you have to just find square root. So what you need is eigenvalues. You construct a diagonal matrix from those eigenvalues, take square root of the diagonal entries, and then you use eigenvector matrices on both the sides. Okay. Other than that, I don't think there is anything difficult in this practical. Thank you.